So we're going to start talking about extrema, meaning minima and maxima. So let's give a few definitions. Let f be a function defined on an interval I. It doesn't have to be an interval, but in most cases, we can restrict our attention to an interval. And let A be in I, a number in I. Then A will be called a maximum for f if it's the largest possible output that f can have on I. So if f of a is greater than or equal to f of x for every x in I. We will also call it an absolute maximum or a global maximum. On the other hand, if A happens to be a maximum only over an interval that surrounds it, then we're going to call it a local maximum. So if f of A greater than or equal to f of x holds just for x belonging to an interval surrounding A, then A is called a local or relative. So local as opposed to global, and relative as opposed to absolute maximum. And we can have a very nice picture here. So take a look at this function. So this function is defined over a closed interval, and you can clearly see that the largest value that it is assumed by this function is assumed right at this point. So this is a global, so maximum output. So this is a global maximum. So that point corresponds to a global maximum. On the other hand, if you look at this, and that, and even that, all of these points correspond to maxima over a portion of the function. So in each case, you can find an interval surrounding each of these points. In this last case, the interval is just on one side of the point. So these points are all local maxima. All of them are local maxima. Please note that maximum has as plural maxima. So all of these are local maxima. So you can clearly see the difference between a global maximum and a local maximum. And we can define the exact same things for minimum and minima. So we can similarly define minimum and or the notion of minimum. And again, we can call it either just plain minimum or global minimum. Or absolute minimum. And also we can define the notion of local minimum. And this would be also relative minimum. Why don't we mark them on the same? So you can see that the minimum is right here. So this point is a global minimum. And then you have other points here, like this one, and this one, and this one, and even this one, that these are local minima. So all of these points are local minima. We also have a word that covers both minimum and maximum. We say extremum. So extremum is minimum or maximum. Okay. Now, here I would like to note that a function does not need to have one minimum and one maximum. Basically, it can have none. But take a nice example like the function sine, and you will realize that sine has infinitely many points at which it has a maximum. So all of these points are maxima, if you like. And it has also infinitely many minima right here. So they don't have to be unique, and they don't have to exist to begin with. So if I take as my function the function x, y equals x on the whole f of x equals x on the defined everywhere on the whole real line, you will see that there are no minima and no maxima, no extrema, in other words. So extrema do not, or local extrema do not need to exist. But if they exist, we want to be able to find them. And the first step that we're going to take is try to identify what can possibly happen in the case of local extrema. So let's begin by looking at local extrema. So in particular, I would like to look at local extrema which happen to be in the middle of the interval. So there, you can surround them by an interval on both sides. So take a look at this point right here, which is a local maximum. And I'm saying local maximum because I don't know how the function continues on the two sides. I don't even want to know how the function continues on the two sides, but I can see right away that it's a local maximum. And what you can notice that was noticed pretty early was that the tangent at that point is horizontal. And the same thing can be said about local minima. So we have our first theorem for today. Actually, this is usually attributed to the famous French mathematician Fermat, that if a differentiable function f of x has a local extremum at an interior point. So when I say interior point, I mean that you can pretty much move a little to the left and a little to the right from that point. At an interior point A, then the derivative f prime of A has to be equal to 0. Now, how nice would it be if the derivative being equal to 0 implies that the point is automatically a local extremum? unfortunately, no such thing is true. And we can give an example. The classical example that anybody gives here is the function f of x equals x cubed. If you take the function x cubed, then what happens is that it's a little flat at 0, and f prime of 0 is 0, but 0 is not a local extremum for this function. So we do understand that in general, points at which the derivative is equal to 0 are going to be important, and they're going to be, and usually something interesting is going to happen at those points. So we give them a name. So if f prime of a is equal to 0, then a is called a critical point of the function f. So this means that we can start by finding where the derivative is equal to 0. And usually interesting things will happen at points where the derivative is equal to 0. It's up to us to figure out what exactly is happening at those points. And we'll try to do that. But why don't we first start with an example? So let's just see how we find the critical points of a function. So as a first example, find the critical points of the function f of x equals to x cubed minus 3x plus 5, defined on all of our. So again, critical points are points at which the derivative is equal to 0. So what we're supposed to do is find the derivative of this function and set it equal to 0. So f prime of x is equal to 0 if and only if 3x squared minus 3 is equal to 0. And this is if and only if 3 times I can factor out 3, x squared minus 1 is equal to 0, which means that if and only if x squared minus 1 is equal to 0, which means that x will be plus or minus 1. So the critical points of f are -1 and -1. And that's it. Okay, let's do one more example. So find the critical points of the function f of x equals x e to the negative x. Let's see. So we have f prime of x is equal to 1 times e to the negative x plus x times e to the negative x times -1. That's what the chain rule gives us. And the question is, how in the world can we find at what points this expression becomes equal to 0? So we wish to solve. So we wish to determine x's such that e to the negative x, I'm not rewriting the number 1, plus x times e to the negative x times -1 is equal to 0. So the trick here is to actually factor out e to the negative x. So if you factor out e to the negative x, what you get is 1 plus x times -1, so that's minus x is equal to 0. And here, the important thing to notice is that this quantity right here, meaning this quantity right here, can never be 0. In general, whenever you consider the exponential function is never 0. So the only way that this can be 0 is if 1 minus x is equal to 0, which means that x is equal to 1. So 1 is the only critical point of f. Okay, so let's not forget that we started this whole business with critical points in order to find out whether a given function has local extrema. And we wanted to talk about local extrema just because it's, in some sense, a way to study global extrema. So our goal is to be able to find for a given function its minimum and its maximum. But it has to be done in this roundabout way where we find the critical points. The critical points, some of the critical points may be local extrema, and then our job is to assess which of these local extrema could be global extrema. So, so what we would like to begin with is a situation where the minimum and the maximum of a function can be guaranteed to exist. And there are not so many cases, but we have one remarkable case. So this case is the case of a continuous function over a closed interval. So we have this beautiful theorem. It's one of the nicest theorems of elementary analysis, and it says the following. If f is continuous, so it's defined and it's continuous on AB, then it has a minimum and a maximum. And the question is, how do we find the minimum and the maximum of the function of a continuous function over a closed interval? And you know, in general, there wouldn't be a general method, but in our case, we're going to also assume that the function is differentiable. And so we make the following remark. So if f is also differentiable on the open interval AB, then the extrema may occur at two types of points. The first type of point is critical points in AB. Why? If you have an extremum inside, so here's AB, let's say, and you have your function and it happens to have an extremum right inside the interval, then by what we said, the derivative of the function has to be 0 at that point. That's why it has to be a critical point in the interior. So if you exclude the case of points in the interior, then the other cases that are left are the points A and B, meaning the endpoints. So points A, B, the endpoints. So these are the only possibilities. And this remark narrows down so much the possible points at which one can have an extremum that almost gives us a workflow on how to find those extrema. So the idea is very simple. Take all the critical points in the interior of the interval AB, take the endpoints, and evaluate your function at those points in order to decide where the function is the largest possible, where it's the smallest possible. Since these are the only candidates at which you can have an extremum, wherever you find it to be the largest, that will have to be the maximum, and it could be at more than one place. Whenever you find it to be the smallest, that will be a minimum. So let's do an example and see how this works. And this is what we're calling optimization over a closed interval. So by optimization, we mean finding either the minimum or the maximum. Usually when you have a concrete problem, minimizing or maximizing a function means to actually optimize it. It serves some purpose. So find the minimum and the maximum of the function f of x equal to x cubed minus 3x plus 5 on the interval from 0 to 3. Okay. Let's do this. Let's see how it's done. So as I told you, it will all be based on testing finitely many points. And the two first points that you want to test, so the two first candidates for extrema are the endpoints. That's why I build the table. And the first 2 points that I put on that table are the endpoints. And then I start doing everything else. And what is that everything else that has to be done? You need to identify, I need to identify the critical points in the interior of the interval 0, 3. How do I find the critical points? So we first consider the endpoints. Zero, 3 and put them on the table. Next, we will look into the critical points in the interior of the interval. Into the critical points. And this is where we have to be careful. If we find critical points that are not in this interval, we should exclude them. In 0, 3. So how do we find those? Take the derivative, 3x squared minus 3, and set it equal to 0. This means that 3x squared minus 3 is equal to 0. We just solved this a moment ago, right? Okay, let's solve it again. This means that x squared minus 1 is equal to 0, and this means that x is equal to plus or minus 1. So now we find two critical points, right? But we have to be careful because the set we're working with is 0, 3, and negative 1 is not in that set. So negative 1 is dismissed. And so we only take one and we put it on our table. So now we're going to evaluate the function at each of these 3 candidates for extrema. F of 0 is 5, right? Easy to find. F of 3 is 27 minus 9 is 18 plus 5, that's 23. And f of 1 is 1 minus 3 is negative 2 plus 5 is 3. Okay, so now it's pretty clear. This is the maximum. We mark it like this, and this is the minimum. And we're done. Okay. This is pretty much one of the standard things that we learn how to do in this context. And it's a good idea to do one more example where, let's not work with a polynomial this time. So example. Find the minimum and the maximum of f of x being equal to e to the x over x on the interval no, actually, that's not what I wanted. So let's do f of x over x is equal to ln of x over x on the interval from 1 to e squared. Okay, let's do this. So okay, same story as before. So start by forming a table and start by putting on the table the two endpoints. So the two endpoints are what? 1 and e squared. Okay. And now let's find the critical points in the interior. So to find the critical points in the interior, we find the derivative of the function, which by the quotient rule is 1 over x times x minus ln of x times 1 over x squared. Now it's a case where we need to simplify what we have. So this will become 1 minus ln of x over x squared. And the only way that a fraction is equal to 0 is if the numerator is equal to 0. So 1 minus ln of x is equal to 0, which means that ln of x is equal to 1. And what is the only number that has natural logarithm 1? You can find it by raising both sides actually to e, and or raising the both sides, having the both sides as exponents with base e. And of course, you're going to get e to the ln of x is x, and this is e. So this is the only critical point. Don't forget to ask if the critical point that you found belongs to the interval under equation. And yes, it does belong to the interval from 1 to e squared. So I'm going to put it in my table, and now it's time to actually figure out whether this function, or where this function has its minimum and its maximum. So when you plug in 1 into the function ln of x over x, what do we find? Ln of 1 is 0. So you find 0 right here. Then what is ln of x, or what do you find when you plug in e squared? Ln of v squared is 2. So what you're going to get is 2 over e squared. Finally, what do you get when you plug in e? Ln of v is 1. So you get 1 over e. So this has to be your minimum. But out of these 2 points, what is the maximum? This is a very interesting question, actually. So you have to compare these two numbers, 2 over e squared and 1 over e. And the trick to understand which one is the largest is by writing 2 over e squared as 1 over e, which is the other number, times 2 over e. What is e? E is 2.718. You don't need to know that much more. It's between 2 and 3. That's what matters, which means that this number is less than 1. So this number has to be the largest, right? Because the other number is what? It's as if you take the number 1 over e and you multiply by something less than 1, so it becomes smaller. It's the largest of the two. So that tells you that this is your maximum. So this is an interesting problem. So you have to play this little game here, but you get your answer. And that concludes the solution of this problem. We found the minimum, we found the maximum, and that's it. Thanks for watching.